Alright, we're almost done with bonding. This will be the last video on bonding. Get out the Kleenex box. I'm sure you're sad. Let's look at the bonding in nitrogen, diatomic nitrogen, because I want to show you an example with a triple bond. So we may be asked to draw the Lewis structure, which would be super easy. I know that nitrogen with 5 valence electrons usually has a pair and 3 singles. But if I'm drawing N2, I usually draw the pair on the outside and then the singles toward each other so that they can pair up and triple bond. 1, 2, 3. Beautiful. Okay, so there's my Lewis structure. Determine the Vesper shape. Well, that's a piece of cake. Whenever you have a molecule with only 2 atoms, we have no other option but to see this as linear with a 180-degree bond angle. Now, sometimes that kind of stumps people, like, well, I don't know, like, what's the center atom? Well, there really is no central atom. The only way you can connect 2 things is with a straight line. Okay, so we got the Vesper shape. We threw in the bond angle. This would be a non-polar bond because I have the same atom sharing electrons, so it's not like there's going to be a partial positive or partial negative. I want to look at the hybrid orbitals needed to describe the bonding in this molecule. Okay, cool. So let's tackle each nitrogen. Each nitrogen has 2 regions of electrons. Obviously, we've got the triple bond in the center. That's a region of 6 electrons. But we also have a lone pair on each nitrogen. Each nitrogen needs 2 regions to put electrons, counting that lone pair. So that's going to give me the sp hybrid orbitals. So again, this looks better in color, doesn't it? The yellow orbitals are supposed to represent the hybrids here. sp orbitals, hybrid orbitals, are 180 degrees from each other. So you're going to have the lone pair in one, and then the other hybrid will overlap in the center. And so we can either do dots or arrows. And there would be 2 more electrons shared. Now each nitrogen also has then 2 unhybridized p orbitals. Whenever you hybridize an s and a p, you'll always have 2 extra p orbitals. So that's what they're trying to show in this picture at the bottom. They're trying to show that here are the extra p orbitals, the extra unhybridized p's. And they're parallel to each other. So here's 2. These guys kind of match up. And then here's the other 2 that are kind of at an angle in 3 dimensions. And these guys are parallel to each other. Now again, each of these orbitals would still have an electron. So if I think about like the original nitrogen atom, here's where I'll find the 5 valence electrons. 1, 2, 3. This other hybrid would have 1. And then the other p orbitals would have 1. I get that it kind of looks like, the p orbital looks like 2 orbitals because there's 2 lobes. But that's 1 orbital. So can you kind of see the distribution of the 5 valence electrons in nitrogen? Because I bet now you can see where this triple bond comes from, right? In the triple bond, we will have a sigma in the center from the overlap. I'll put like the overlap of those hybrids. We'll have the extra pair in the other hybrid. And then the other parts of the triple bond come from the overlap of those unhybridized p orbitals. So these guys, this guy and this guy, they each maybe had a valence electron. And we don't know if it's in the top lobe or the bottom lobe. I'll just kind of draw them in the top lobe so they kind of look close to each other. So this unhybridized p orbital is going to kind of bend in toward each other, again, to overlap. So this would also give me the sharing of 2 more electrons. And then I have that other unhybridized p orbital. So maybe we'll like throw one in here, one in there. And again, I don't know if it's in this lobe or it could be in the back lobe. That we don't really know. But then these extra orbitals would also overlap and share 2 electrons. Here's your triple bond. Here's your sharing of 6 electrons. Cool. Make yourself this note, a triple bond. Will always be 1 sigma and 2 pi bonds. So I wanted to do an example with a triple, something like nitrogen. So even if I didn't have all these crazy 3-dimensional orbital pictures to look at, if I had the Lewis structure, I could tell you that there's 1 sigma and 2 pi. Now it's good to have these bubbly 3-dimensional orbital pictures because that really shows me the correct angles and it shows me the shape of the orbitals and the unhybridized p's. I mean, that's good stuff. But anytime I see a triple, it's going to be the overlap of hybrid orbitals, sp hybrids, and then 2 unhybridized p orbitals. The unhybridized p's will form the pi bonds, the 2 pi bonds. And then the overlap of the sp hybrids will form the sigma in the center. So it's always a sigma and 2 pi's for a double bond. Now if you look at the other parts of the study guide, we should make note, when we play with molecular model kits in class, one of the best days of the year, right? You'll notice that around a single bond, you can rotate and like spin the carbons or whatever atoms it might be, but you cannot do that around a double or a triple. So they might have a structure and say something like, is rotation possible between the carbon-carbon double bond or the carbon-carbon triple or any kind of double or triple for that matter? And we'd say no. And that's going to help when we can really like play with these molecular model kits, because then you can try as much as you want, but you can't like twist the structure without breaking the double bond. So this is something that they again could ask us about, and they want to know, like, can you really visualize this structure? And we'd say no, rotation cannot occur around double or triple bonds, just single bonds. Now this you're going to love because you can cross it off. You do not need to do any hybrid orbitals that involve D's. So we're not going to do this D sp3. We're not going to do this example. Or we're not going to do this one with 2 D's. The AP test will only ask you to understand hybridization of sp3, sp2, sp, and they do expect that you're familiar with the terms like sigma bond, pi bond, and then that little piece on rotation. But you can cross all this off in your study guide. You do not need to do any hybridization that involves d orbitals, so that means you're done. There it is. Anything you could ever want to know about bonding.